Hi. I'm going to resume talking about classical small cancellation conditions, and we'll see their consequences, some important consequences of them today. So last time we learned about two complexes, Van-Kampen's lemma pieces, and we defined the C prime and C small cancellation conditions. I'll just quickly remind that X is C prime of 1 over P if any piece P in the boundary of R for any two cell R of X has length that is small as a proportion of the total boundary length. Okay, that's C prime of 1 over P. X is CP if for any two cell R of X, the boundary of R is not the union of less than P pieces. Okay. And one of your exercises will be to come up with a different characterization of that in terms of disk diagrams. Here we have P at least 3. Now we're going to talk about flowers a bit. We're going to say that X is TQ, Q at least 3, if every reduced Jasmine diagram, which I'll define in just a moment, in X. So here's a Jasmine diagram. Fine.
That's not pizza pie?
I like flowers. You know, you
Put flowers at the end of this thing.
you know, you should have complained when I wrote my master's thesis, Donnie. So that's a Jasmine diagram. In X, so we asked that every such reduced diagram has at least Q petals. Okay. Where a Jasmine diagram is a disk diagram where D has a unique interior vertex, call it V, and the degree of V is at least 3, and no edge has both ends at V. Okay. That should suffice to restrict to this class where we have at least 3 petals. And what are petals? Petals are the two cells. All right. Let's look at some examples. C6T3. You take this underlying graph you glue on these, you glue on this single 2-cell along the indicated boundary path. And that's going to give you a C6 T3 complex. And that's what its universal cover is, the hexagonal tiling of the plane. And that's maybe sort of the prototypical model of a C6 space is the hexagonal tiling of the plane. C4 T4, the square tiling, and the standard Z-squared presentation. And if you cut the cell in half, this square in half, you get this presentation, which is C3 T6, and well, that's your triangular tiling of the plane. That's your prototypical model of C3 T6. That's what you should think about. Oh, and another example. We have this guy, which you can describe in the usual way as this presentation. And this is, well, C prime of 1/7 T8. Okay. Here's an exercise. Let x hat to x be a covering map of two complexes. Then x is C prime of 1/P if and only if x hat is C prime of 1/P. Same holds for the CP condition and the TQ condition. Does the C and CP stand for something?
The T is just to remind you of that picture that we fell around one vertex.
Is that right? Okay.
It's good for now. It doesn't matter. Keep going.
Yeah, I never thought about that question, but C for cancellation makes sense. Okay, another exercise, and you know, I state this now so that well, so that you're aware that this is possible and not hard. Find an infinite family of words Wn in A and B such that AB or the presentation AB with all these Wn's as relators is C prime of 1/6. And last exercise that I'll mention for now. Yeah, and this is very important. Show that if D is a reduced this diagram in X, which is CP TQ, then D itself is CP TQ. Okay, so it's good to know that that's true, and you can think about how to prove it later. Okay, any questions about these definitions? Yeah.
Interior vertex being that's been diagram.
Interior vertex, like what do I mean by interior vertex? Yeah, so an interior vertex of a disk diagram it is one that's not contained in the topological boundary of the disk diagram inside of S2. Other questions about these conditions? Oh, I meant to remind everyone that the notes for this are up at sc.nimahoda.net. So you can follow along there as well. So next topic. Well, what do we get when we have a CPTQ complex? I'm going to tell you about the combinatorial Gauss-Bonnet theorem and Green-Linger's lemma. Okay, so let D be CPTQ disk diagram. I claim that by merging and subdividing edges of the one skeleton, so we're going to sort of recellulate the underlying graph here, we can obtain an associated CPTQ disk diagram D prime satisfying some additional conditions. Condition 1, two cells have boundary paths at least length p, and 2, including the boundary ones, 2, any vertex v of degree 2 is a boundary vertex of D contained in the boundary of a two-cell R with boundary length equal exactly to P. Okay, and okay, P prime a normalized disk diagram associated to D. Okay, let me give an example that'll make clear exactly what's going on. Basically, just deleting vertices of degree 2, we're merging the two edges there, and then we're adding some degree 2 vertices back in. Okay, so let's do C6 example. We have this diagram that eliminate. Okay, so first we get rid of all the vertices by merging. I get the same there. Yeah, thing there. Yeah. And then because it's C6, we're not happy that there are some, of course, any interior T cell is going to have boundary length at least 6 because the original diagram was C6, right? But you know, for some reasons that will become clear a little bit later, we're not happy that some of those boundary two cells have boundary length less than 6. Okay, so we're gonna add some back. Guys. 2, 3, 4, 6. So each of these degree 2 guys appears on a boundary cell, and that cell has exactly P boundary length. Okay, well, here it happened that each one of those needed exactly 2 more, but that's not always going to be the case. Okay, and let me remark now that interior edges, so this is D prime, this is D, interior edges of D prime correspond to maximal pieces. All right. Well, these normalized disk diagrams are in a state where we can think about them in a kind of geometric terms, which will help motivate some of the formulas that we're about to see. So let me give this geometric idea. We're going to metrize the 2 cells of D as constant curvature 2 cells. Constant curvature, regular polygons of side length 1 and angle 2 pi over Q. Okay, so could you speak louder a bit? Why does this graph why does this satisfy the C3 condition? Yeah. This one. Yeah. Why does it? Okay. So well, C3 condition says that no T6. Sorry. So the reduced Jasmine diagrams here are these cones on hexagons, right? That does look a bit more like a pizza, angled pizza. They should make them like that. Yeah. So this guy has degree at least 6. There are 6 slices or petals here. So we can't get a diagram like this with fewer slices. This is the universal cover. Yeah. But as one of our exercises told us, covering maps have satisfy the same small cancellation properties as the original space. But also, I mean, you can sort of just think about the diagrams in here that have this shape and are reduced, right? And think about why this vertex has to have always degree at least 6. That's the answer. Any other questions? Right. Because if it had lots of interior pieces, you left it as it was. You were happy, right? You were happy. You didn't go and throw some degree 2 vertices on it. Yeah. Condition 2 says any vertex of degree 2. If you see a vertex of degree 2, yeah, it had to have been on the boundary of a 2 cell. Yeah. So right, so we have some idea about how to view these things geometrically. Okay, so we're gonna well, that doesn't look like it's the same length, does it? Okay, we're gonna treat the cells as constant curvature polygons where all of the side lengths are 1 and all of the angles are 2 pi divided by Q. Okay, all the same angles everywhere. Now, by the Gauss-Bonnet theorem, the classical one with corners, the total curvature in the interior of a two-cell R of D prime is kappa sub q of R is equal to 2 pi minus the boundary length times pi minus 2 pi over q. Now, if you don't know what this Gauss-Bonnet theorem is, it doesn't really matter. Really, we're just using it to motivate where this equation is coming from. There's some geometric source for it, but from now on, this is just going to be a definition for us. Okay, but if you're familiar with the Gauss-Bonnet, well, that's 2 pi times the Euler characteristic of a disk, and that's the number of turns, and that's the number of turns we have on the boundary and the amount of turning that we do at each turn. So that's the total curvature on the boundary. Now that's at most 2 pi minus p times pi minus 2 pi divided by q, which I'm going to define that as a. So I'm just going to that's for later, but I'm doing it now. This value. Okay, and this p because our cells all have length at least p. Okay. Boundary length. So the value on the right is less than or equal to 0 if and only if 1 over p plus 1 over q is at most half. And this is what we call the Euclidean case. And it's strictly less than 0 if and only if 1 over p plus 1 over q is strictly less than half. And that's what we call the hyperbolic case. Okay, and I made a note to myself not to erase this. I'm going to draw a little graph here. Okay, so if I have p and q, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7. And I consider all these are all of my possible values. And if I draw, let's see, C3, T6 is on there, C4, T4 is on there.
You can't see the difference between that and the other top. So.
Green is bad. Green on green is no good. Thanks. Pink on green, I think. Pink on green, I think is good, right? Okay. So let's do that. So what I'm drawing there is 1 over p plus 1 over q equals half. Okay. So the Euclidean cases are all the ones below this line. The minimal Euclidean cases are the ones that are on the line. Everything that's Euclidean also satisfies one of these three conditions because these conditions are monotonic, right? So you only really need to consider C3, T6, C4, T4, and C6, T3. Okay, so that's why these are the three really important cases. Somewhat the if you want to bound all the hyperbolic cases from below, then maybe you care about these guys as well. That's all right. I'm going to state the combinatorial Gauss-Bonnet theorem. Let X be a two complex. Then 2 pi times the Euler characteristic of X is equal to the sum of the vertex curvatures, which I haven't defined yet, but I will in a second, plus the sum of the two cell curvatures, which is defined over there, where vertex curvature is defined as exactly the thing it needs to be, which is 2 pi minus pi times the degree of v plus 2 pi times half minus 1 over q times rho of v, where rho of v equals the number of corners of two cells at v. Okay, and the proof is an exercise. Okay, basically involves redistributing the Euler, the contributions that cells make to the Euler characteristic, so that the contributions that are left are exactly these curvature values. And that's, I geometrically motivated the curvature of two cells. Well, the curvature of vertices here is just defined as exactly what it needs to be to make this work. So okay, let me make a remark, and then I'll see if there are questions. In the case of a non-singular disk diagram, that's one that's homeomorphic to the ball, the curvature of a vertex, there's two cases, is either equal to 2 pi minus 2 pi over q times rho of v, if v is in the interior of D, or it's equal to pi minus 2 pi over q rho of v. Well, otherwise, if v is in the boundary. So in this case, vertex curvature is less than or equal to pi minus 2 pi over q, which I'm going to define this as b for use soon, when v is in the boundary, and if d is tq, then this is less than or equal to 0. Okay. For v in the interior. Thus, we have that 2 pi is equal to, well, I should say 2 pi times 0. 2 pi is equal to 2 pi times the Euler characteristic of the disk. Disks have Euler characteristic 1, which is equal to well, we've got that right above. So I'll say this is at most total boundary curvature of vertices plus curvature of two cells. Any questions about the combinatorial Gauss-Bonnet statement? Mr. Mark, can you speak up, please?
Complex
Yeah.
has negative curvature in the sense, does it have a cat minus 1 metric?
No, not necessarily. So for example, you could have multiple copies of a disk glued to the same circle, and that's both simply connected and CP, and C prime 1 over P and TQ for all values of P and Q, and yet it's definitely not contractible. So it's not.
Yeah.
They're related. And some of the relationships will become clear later. Yeah. But this is similar territory to right. This is all sort of notions of non-positive curvature. Yes.
What if you don't do the disk?
What if you don't do the disk thing? Yeah, I mean, you would have to tell me. I mean, sometimes yes, and sometimes maybe no. But yeah, yeah. I mean, even in the hyperbolic cases, I mean, like, well, even in the hyperbolic cases, you got overlapping pieces and funny kinds of things are happening, and it's not exactly clear how you're going to metrize your cells in order to, right? You don't, for example, if these are polygons, you don't want to be gluing them along pieces of length more than 1, right? So then you would have to like flatten some, you know, if you have pieces of longer, you'd have to flatten them, and then it's right. So yeah. Okay. Those are advanced. Oh, I was about to erase what I don't want to erase. Nobody stopped me. Okay. What did I want to say next? Yes. When D is normalized CP/TQ with 1 over P plus 1 over Q less than 1/2, we have that the curvature of 2 cells is at most A, with A defined over here, with A, in those cases, it's actually going to be negative. Okay, so 2 pi is strictly less than the number of vertices of the boundary times B plus the number of 2 cells of D times A, which is at most the boundary length times B plus, well, we'll call this the area of D. We'll notate that as like that, times A, and we get a linear bound on the area of the disk diagram. Did I miscalculate? No. Okay, so well, what's a consequence of linear isoperimetric function? Hyperbolicity. So we have the following theorem. If X is a simply connected CP/TQ complex in hyperbolic case with 1 over P plus 1 over Q strictly less than half, then X has linear gain function, and as a consequence, we get that pi1 of X is hyperbolic for a finite CP/TQ complex X with 1 over P plus 1 over Q strictly less than half. When did we start, by the way? How much time do I have? All right. So we'll get to Greenlinger's lemma for maybe C4, T4, and we can read C6 from the notes. Okay, so yeah, so those are the hyperbolic cases. What can we do with this for the Euclidean cases, which are also of great interest? Let P equal Q equal 4. So we're going to be in C4 T4 world. Let D be non-singular C4 T4 disk, and let D prime be a normalized associate. Then we can do a slightly different computation using combinatorial Gauss-Bonnet. So for V and the boundary of D prime, the curvature is equal by definition to pi minus half pi times rho of V summed over all V in the boundary. The cells in the interior vertices have non-positive curvature. And this is equal to V, or this is at most V in the boundary of D prime, where rho of V equals 1 times pi, or pi over 2 minus pi over 2 times those guys that have rho at least 3. Okay, so what that gives us is that 4 plus the number of boundary vertices with degree at least 4 bounds from below the number of boundary vertices of degree 2. So what's really important for us at this moment is that 4 bounds from below the number of, yes. Yeah, so we'd like to understand some properties of the Euclidean case C4 T4. And to do that, we're going to understand what C4 T4 disk diagrams look like. And this computation is going to tell us things about the geometry of C4 T4 disk diagrams by telling us, well, there are at least 4 vertices of degree 2 on the boundary. Okay. And if we recall, in our definition of a normalized disk diagram, those degree 2 vertices were like things that we added to, like, because, right? So, yeah. Other questions? Okay. Yeah, so 2 cells with degree 2 vertices in our normalized disk diagram D prime come in 3 types. Like we left these dummy vertices there to kind of indicate things about the geometry for us later. So either you have 2 internal pieces, okay, or you had 1 internal piece, or you were a single 2 cell. That's the other possibility. Okay, and now I'm going to define shells. An I shell of D is a 2 cell R such that the boundary of R is a union of two subpaths, P and Q, such that P is a boundary path in D. Okay, so P to D factors as P to the boundary to D, and Q to D has interior image, except at endpoints, and is the concatenation of I pieces of D. Okay, well, let's look at an example. So that is a two shell. Okay, so that part is what do we call it? P, that's on the boundary, and then that part is Q, or it's the image of Q in D. And that's a one shell. And I'll remind us what a spur is by putting that there right now. That's a spur. Okay. And I'll just, as an aside, I'll say, not really an aside, but if you have something like this, then that's also considered a one shell. Okay, that's now I can state Green-Linger's lemma in the C4T4 case. C4 T4 Green-Linger, let D be a C4 T4 this diagram. D is a single two cell, or D has at least two spurs and or one shells, or D has at least spurs and or I shells with I at most 2. And then there's second part that moreover, if no spurs, one shells, or two shells, sorry, no spurs and one shells, and at least 6 two shells. Okay. And so basically, this is how you do it for non-singular disk diagrams that have no cut pieces. And then you have a little induction on cut pieces and then an induction on cut points. And that's how you get that. Okay. And as a corollary, any C prime of 1/4 T4 presentation is Dane. And what that means is if you have a trivial word of your group, then you're going to find a subword that's common with a cyclic conjugate of one of your relators or their inverses. And that subword will take up more than half of your relator. So you can replace that subword with the rest of the relator and simplify your word. And this is a way to get a linear time algorithm for the word problem. Okay. Of course, I think now it's known that all hyperbolic groups have those, right? But not necessarily the presentation that you have. So this is. So there's a similar, there's a Greenlinger also for C6, T3, which involves spurs, 1 shells, 2 shells, and 3 shells. I'll skip over that, but it's in the notes, sc.nimahoda.net. That'll be up for maybe a week or two after the course. And I wanted to finish by saying something about quadratic isoparametric function. Let me very briefly take 1 minute to say that. So these computations that we did told us that there's a certain prevalence of shells along the boundary of a Euclidean CP-TQ. Well, at least, well, it's true for C6 and C4T4 disk diagram. And somehow there's a sort of there's more of them than, like, you know, let me rephrase that. You have a CP-TQ disk diagram. You peel away your outer layer. You peel that off. But what you're left with inside is also CP-TQ disk diagram. Okay, so it's got shells, right? Like this. Now, if you think about the fact that the original disk diagram is CP-TQ, that means that you have these things on the inside that don't have a lot of pieces with respect to the interior disk diagram. So that means that they're going to have to have pieces, more pieces with respect to the outer layer. That means that the boundary length of the original disk diagram is longer by some uniform constant amount than the boundary of the interior disk diagram. Okay. Now you keep peeling away these layers. They're getting shorter and shorter by a uniform constant amount. So you're done after a linear number of steps. Oh, sorry. Yeah, sorry.
Should
Yeah.
be at least 4. Let's see.
Thank you. Yeah. 6 is the C6 case. Yeah. Thanks. So that's the idea. You got a linear number of steps. Each step is moving a number of 2 cells that's linear in the original boundary length of the disk diagram, and linear times linear is quadratic. So Euclidean case, CP-TQ disk diagrams have a quadratic number of 2 cells in the length of the boundary, and that gives us our quadratic isoparametric function for CP-TQ or groups with a CP-TQ presentation. So that's all. Sorry for going over.
This to that like a phi 1x decisible word. Is it true that, like, if you have say like any bound on the area of the this diagram, then you have like a simple word problem?
Yeah, if you have a computable bound, and a quadratic function is a computable bound. So that's the most important consequence of what I just said, is that, you know, groups with CP-TQ presentation, Euclidean case, have decidable word problem. Yeah, thanks for pointing that out.
Won't happen in the future. So eat your vegetables, broccoli, all of it.
So this fluctuates based on